Welcome again, guys. In this video, we're going to go through gluconeogenesis as promised. And what you have to know about gluconeogenesis is that the reason behind glycolysis in the previous video was that there was high levels of glucose in circulation. But time has passed and the tissues has used up that glucose. So remember that we had said that the liver, the excess of glucose that was before, storage that in the form of glycogen. So now, by breaking that glycogen can go out and go to other tissues. And remember that glycogen is the main storage polysaccharide in animals, and that it has alpha-1,4 and alpha-1,6 linkage. And it will start breaking the alpha-1,4 in the alpha-1,6 change. So when it has 4 subunits, it will take 3 of them and place it in the alpha-1,4, and the one that remains from the alpha-1,6 chain, it will use another branching, a debranching enzyme, and it will form glucose 1-phosphate, and from that glucose 1-phosphate can be converted into glucose and then go to other tissues. But also, the cells takes advantage, in this case a hepatocyte, of everything that it has. And if it has intermediates that can return to be, in the process to be glucose, it will do it. The problem is that there are steps that are irreversible in glycolysis. So what it does, it will have to use another enzymes in that steps that either ATP was used as an energy input, or there were high energy intermediates that were the ones that donated the phosphate to ADP to form ATP. In that steps, the cell is gonna use another enzymes in order to proceed backwards. In this case, for gluconeogenesis, it can start in any intermediate, but we're gonna start from the last one, from pyruvate. Pyruvate can be converted, cannot be converted directly into PEP in this step. It will first be converted into oxaloacetate. Through an enzyme called pyruvate carboxylase. And in this step is, it will need a lot of energy input, in this case in the form of ATP, to make this step proceed. In this case, it will use 2 ATPs. And something else that you have to know is that pyruvate carboxylase uses a biotin cofactor. That, if you remember, is the one that moved the CO2 from one place to another. And after that, oxaloacetate can be converted into PEP by an enzyme called PEP carboxykinase. That also needs the input of energy to proceed forward, but in this case, in the form of GTP. And we are starting to see that gluconeogenesis is very expensive, but overall, still, the whole pathway is favorable. And this step in particular, it is an oversimplified version of this step. If you want to see the full connection before this step and how it is connected from also the cytosol to the mitochondria to come with the intermediates before, and depending where it starts with what molecule, it will do more steps or less steps, where for that you would have to check out the metabolic map with hormonal stimulation that shows this step in very, very detail. because this is an oversimplified version. And from here, once we form the phosphoenol pyruvate, we can use the same enzyme, the same enolase, to form 2-phosphoglycerate. Here, the same phosphoglycerate mutase to form the 3-phosphoglycerate. Here, the same phosphoglycerate kinase to go through 3-phosphoglycerate to 1,3-phosphoglycerate. And you might say, hey, stop for a minute. What about that high energy intermediate that you talk about? Yes, you are right. There is a high energy intermediate that pushes this step to go forward. But in addition to be also favorable, it is reversible also, because this step, it is coupled with this step before. And because this coupling and the use of this, because this intermediate is used right away, the coupling of these two reactions allow to be this step reversible. And for that, to explain it and getting to the why and the reason why that happened, I recommend you to see the biochemistry thermodynamics video, so you can have a reference of what is the reason behind it. And from 1-phosphoglycerate, it can be converted into G3P, and while G3P can be later converted into fructose 1,6-biphosphate through the same allolase, and fructose 1,6-biphosphate can be converted into fructose 1,6-biphosphate, in this case by fructose 1,6-biphosphatase 1. And as the same as phosphofructokinase 1, remember that I said in the last video, this is not hormonally stimulated directly. There is another one also called fructose 1,6-biphosphatase 2, that I'm going to explain in a minute. But for that, I'm going to leave it for last in this video, so we can go more in detail. And in this step, we form fructose 6-phosphate, and we can use then the same glucose 6-phosphate isomerase to form glucose 6-phosphate, and glucose 6-phosphate can be converted into glucose with the help of glucose 6-phosphatase. And take the logic behind these two phosphatases. What are they doing? Well, removing the phosphate, in this case, doing the reverse of what the one in glycolysis did. And on here, I said I was going to explain something. On here, when we have the glucose, through this step in gluconeogenesis, as long as exokinase is in the cytoplasm, because remember, glycolysis happens in the cytoplasm, as long as this enzyme is here, all the glucose that is entered, or that we are like transforming from glucose 6-phosphate into glucose again, it will, well, this enzyme is going to also try to do its job. It's going to try to form glucose into glucose 6-phosphate and trap it again. And that is a problem. That is a conflict of interest between the two enzymes. So what the cells does is that it will take this exokinase 4 and it will send it into the nucleus. By sending it into the nucleus, remember, into the nucleus there is not glycolysis. So right now hexokinase 4 cannot be found in the amount of concentration that will compete against this enzyme. So by being trapped there, this glucose 6-phosphatate can transform many, many more glucose 6-phosphate into glucose. And once we have a lot of glucose concentration inside the cell, but in the cytoplasm, this glucose, remember, the glucose transporter can recognize it and will send it out. And that glucose will go into circulation and go to the tissues that are in need of that glucose for the production of energy. And after that, well, we can return here. And the reason behind it is that fructose 6-phosphate can also be converted into what is called fructose 2,6-biphosphate through Here's a through, in this case, fructose, phosphofructokinase 2. And this fructose 2,6-biphosphate can return to fructose 6-phosphate through fructose 1,6-biphosphatase 2. So the thing with these two enzymes is that they are kind of in a dimerized, they are together. And in this case, fructose 1,6-biphosphatase 2 and phosphofructokinase 1, their activation or deactivation depend on the phosphorylation of a serine, the amino acid. So if that serine is phosphorylated, fructose 1,6-biphosphatase 2 will be activated. If this is activated, the fructose 2,6-biphosphate that this step would create, it will make it again fructose 6-phosphate. And you might say, well, and what is the ground thing with that? What happened is, in order to phosphofructokinase 1 to be activated, it needs fructose in further activation in very high rate. It needs fructose 2,6-biphosphate concentration to rise to go allosterically and make it more active. And that is done when this phosphate is dephosphorylated. When that serine is dephosphorylated, phosphofructokinase 2 will be active. If this phosphofructokinase 2 is active, it is going to transform more fructose 6-phosphate into fructose 2,6-biphosphate. If this happens, well, this is the thing. This will further activate phosphofructokinase 1. And this phosphofructokinase 1 will push forward this step, fructose 6-phosphate. And once we have fructose 1,6-biphosphate, this, remember, that is a positive feed-forward activator towards pyruvate kinase that makes this step the rate-limiting step of glycolysis. And whether this phosphorylation or dephosphorylation happen, it come in hand with the hormonal stimulation of insulin and glucagon. And in this case, glucagon is the one that promotes the activation of fructose 1,6-biphosphatase 2 through its phosphorylation of the serine. To have less of this here, so by having less, there is less activation of phosphofructokinase 1. So this enzyme is not going to be that active, and this step can happen. But if it is insulin will promote the dephosphorylation of the serine and the activation of phosphofructokinase 2. Phosphofructokinase 2 will activate it, form fructose 2,6-biphosphate. Fructose 2,6-biphosphate activate this phosphofructokinase 1. One last thing about the hormones. Remember that in this case, it is not like insulin and glucagon come here and bind. What they do is that they are peptide hormones. Peptide hormones binds to membrane receptors that create cascades that send molecules to either activate or deactivate by creating conformational changes in the enzymes. In the case of glucagon, remember, it's a G protein coupled receptor that what it does is that after the cascade has multiplied, it will make the catalytic subunit of pKa to come and, well, do this job, not glucagon. It is going to be the catalytic subunit of pKa. And insulin, remember that it binds in the cellular membrane into the tyrosine kinase receptors. In the tyrosine kinase receptors, the intracellular signal is the one that makes this possible. And well, guys, I think that is all. Good luck studying, and check out the metabolic map with hormonal stimulation that shows everything connected in very detail. It's a little bit long, but it's worth it. And next, we are going to do the thermodynamics video for biochem. Good luck.